Very good afternoon and warm welcome to this live session. I am Dr. Vaibhav Pandit and today we are going to discuss the topic from the subject electromagnetic field theory. The topic here it is titled Maxwell's equations here. So Maxwell's equation is really very important topic to electromagnetic field theory here. It is basically based on whatever we have learned into the static electric field. Generally we term it as electrostatics, and then the steady magnetic field. So Maxwell's equation is basically a set of four equations. So two equations are based on to the understanding of electrostatics, and next two equations are based on to the understanding of steady magnetic field. And in this set of Maxwell's equations, thereupon we have a relationship between the electromagnetic field and magnetic field also, electric field and the magnetic field. So very first of all I will show you the set of Maxwell's equation, and then we will have few of the practice problem based on to this particular topic here. So Maxwell's equation, we have the different kind of sets we can vary, but the most popular and the realistic one is the Maxwell set of equations for we have the time varying fields here. So here we have the first equation denoted del bar cross of E bar is equal to minus del B by del T. I will show you first of all the four equations and then I will come for the explanation here. This is the second equation denoted by del bar cross of H bar is equal to J plus del D by del T, and next to that we have del bar dot of D bar is equal to rho V, and lastly del bar dot of B bar is equal to 0. So here I am orally saying that del bar cross of E bar, B bar. So bar is just the representation to show that this is a vector quantity. So now here we have the equations represented like this, where bold casing is used for representation of the vector quantities, and whatever the operations here you see, so this is based on to the vector quantities here. So I just tell you these are the four equations, and these equations are having the representation by the use of differentiation here. So most of the time the Maxwell's equation, the differential set, is nothing but these four equations. There it is also another name to this set, that it is point form here. So next to the differentiation set of the Maxwell's equation or the point form here, we have the equivalent representation by using the integrals here. So we have the first equation, that it was del bar cross of E bar is equal to minus del B by del T, that is represented as closed line integral E bar dot of dl bar equal to minus del B by del T. Whereas the next equation, what it was, del bar cross of H bar equal to J plus del D by del T, here it is represented by the closed line integral H bar dot of dl bar is equal to surface integral del D by del T dot multiplication with ds bar here. Whereas the third equation is represented as closed surface integral d bar dot of ds bar is equal to the volume integral rho v dv, and the last equation is represented closed surface integral b bar dot of ds bar, and this is equal to 0. So now I will explain you what is the behavior of electric and magnetic field described by these of the equations here. So first of all I will let you know that capital E is representing the electric field intensity. It is conveying the information regarding how much strong the given electric field is. So electric field is existed due to the static charge here. So depending on the magnitude of the static charge, it will be the strength of the electric field here. So electric field is mostly described by capital E, electric field intensity. Now in this equation you see the electric field on the left hand side here. Now next to that, we will come to the another parameter that also describes the electric field here. So that particular field is denoted by capital D here. So capital D is the electric flux density. We know that whatever the positive charge is there, so as per the understanding here, there are certain electric flux lines getting generated onto the positive charge here, and they are searching for the negative charge whereupon they can terminate here. So these many number of electric flux lines with respect to a certain surface area of a plane here, this is nothing but the flux density, electric flux density, and that it is denoted by capital D. So capital E and capital D are the two parameters belonging to the representation of electric field. Next to that we have two more parameters here. Here we have H. So H is magnetic field intensity. So as capital E describes the strength of electric field in terms of capital E. So in the similar way, the strength of magnetic field which is in existence because current carrying component here is denoted by capital H. So E is electric, H is the equivalent magnetic field intensity. Next to that we have capital B. So capital B is magnetic flux density. So for any magnet, let us say for example the bar magnet if you have here. So for the bar magnet from the north pole there are originating the magnetic flux lines and they are ending onto the south pole. So these are the magnetic flux lines. So when the number of magnetic flux lines divided by the surface area of a certain plane under consideration is computed, it is nothing but the magnetic flux density denoted by B. So I have introduced you to the four vector quantities that describe electric and then the magnetic field. So electromagnetic field in total here. Now in addition to these, there it is another representation of a vector quantity. Here I encircle this, here it is. So capital J is the conduction current density, and of course it is the cross sectional conduction current density here. So how much amperes of current is crossing a certain cross section of a conductor here, it will be having the area. So that is nothing but the cross sectional current density, amperes per meter square, it will be the measurement unit for it. Whereas rho v is the volume charge density measured in terms of coulombs per meter cube here. Now I will describe you the things here. See, in the first two equation on the left hand side you see here this set is equivalent to this set. So this is the representation in point form, also known by the differential form, whereas here it is the representation in the integral form here. Now you see this particular operation, del bar cross of. What is del? Del is the vector differential spatial operator here. So del bar cross of a certain vector quantity is nothing but the choral operation. I have already my lectures available on the online platform, thereupon I have explained that if for a certain quantity there it is a rotational behavior, so we can say that the curl operation that can be denoted by the del vector and the vector quantity here will be a non-zero thing here. So as we know that if there it is a certain point charge, so from that point charge, considering the positive magnitude, we consider that there are the electric flux lines originating from that particular point charge and they are going in all the possible directions to search for a negative charge where they can end here. So this is not a kind of rotation here. So when we are talking about the static equations, this there, first of all we find it to be equal to 0. But when we have the time varying fields, so with the change in time, the quantity when varies here, the observation is that this is equal to minus del V by del T. So B is the magnetic flux density here. So the explanation I have already provided in the previous lecture. And now when we talk about the current carrying component like this, if the current is there in the upward direction, so that time there are certain lines of forces that we call flux lines. They are having the circulating orientation surrounding to the current carrying conductor here. So this is what the rotation. So ideally for the static fields also, here we have del bar cross of H bar is equal to a non-zero thing, and it is found to be the addition of the two current densities here. First one is the conduction current density J bar, and second one is the displacement current density that can be denoted by del D by del T here. So because of the rotational operation here, the curl operation here, these are the two equations. The first one is concerning to the rotation of the electric field intensity, whereas here it is concerned to the rotation of magnetic field intensity here. Now next to that we have these two equations where on the left hand side you see del bar dot of a vector quantity. So it is the representation of the divergence here. So divergence is nothing but either the expansion or the contraction here. So initially the volume of a certain closed surface here, and with the time changes it becomes this much. So it is the expansion. So the divergence value for the vector quantity associated to this particular example here will be a positive thing here. So with respect to the electrostatics here, according to the Gauss's law, so it is equal to the volume charge density denoted by rho v in terms of coulomb per meter cube here. So this equation has come up from the Gauss's law here. And as we see the current carrying element, there are the lines surrounding to it represent flux lines. So this is not the expansion. So that is why the divergence of V is equal to 0 here. So these two equations are represented by using the divergence operation here, whereas these two equations are represented by the curl operation here. Now this is the equivalent form in the integral form here. Now here we have the del bar cross of H bar is equal to this one. So this is from the Ampere circuital law, this is from the Gauss's law, and these are the two equations those have been derived as the equivalent to the quantities according to the Ampere circuital law and that of the Gauss's law here. So I hope this much of introduction to the set of Maxwell's equation for time varying fields is enough, and with the understanding of these four equations, now we are ready to solve. So let us have first problem statement here. So we start with, let mu is equal to 3 into 10 raised to the power minus 5 Henry per meter, comma, epsilon is equal to 1.2 into 10 raised to the power minus 10 farads per meter, and sigma is equal to 0 everywhere. So if h is equal to 2 cos in the bracket 10 raised to the power 10 into t minus beta x, bracket is completed and it is multiplied by a z here. This is measured in terms of ampere per meter. Use Maxwell's equations to obtain expressions for capital B, capital D, capital E and beta. So this is what the problem statement here. Now you see in the given problem statement, the value of mu is provided. What is mu? Mu is permeability of the medium. Any material medium can be described with the help of the three quantities. So one is the sigma, second is the mu, and the third one is epsilon here. Sigma is the conductivity of the material medium. Mu is permeability of the material medium measured in terms of Henry per meter, whereas epsilon is permittivity of the medium measured in terms of farads per meter. So how permissible a certain material medium is for the conduction of electric field through it, that information is provided by epsilon, whereas how much the given material is permissible to the conduction or the propagation of the magnetic medium. So magnetism, that is nothing but the mu here. So mu value is provided, epsilon value is provided, and we are provided with sigma is equal to 0. So this is not a conductive medium, it is a non-conductive medium here. So this is everywhere. Now we are provided the representation of vector representation of capital H here. So capital H is nothing but the magnetic field intensity expressed as 2 cos 10 raised to power 10 t minus beta x here. Beta is the phase shift constant here. Beta is the phase shift constant, and here in this problem statement we have to make the use of Maxwell's equations that just now we have been introduced to, and we have to obtain the expression for capital B, capital D, capital E, and finally the beta. So let us start with first of all determining the expression for capital B here. Now we are well known to the fact that capital B is nothing but the magnetic flux density, and capital H is the magnetic field intensity. The relationship between the magnetic flux density capital B and magnetic field intensity capital H is given by the equation. Here we have capital B is equal to mu into H. So in this problem statement we have already been provided what the vector H is. So we have this value to be known value, and the constant mu, there it is required to have multiplication to this H. So this is also a known value. So a multiplication of two known values will be quite very much simpler here. So for obtaining the expression for capital B here, just substituting the values of mu and that of the capital H. So it will be taking the form here. We obtain 6 into 10 raised to the power minus 5 in multiplication to the cosine of 10 raised to the power 10 into t here minus beta into x, bracket is completed, and this is multiplied by a suffix z here. So as this is magnetic flux density, it is measured in terms of Tesla. So this is what the answer, you can make the outline to. So this is the answer for capital B to be the magnetic flux density here. Now next require capital D here. So for determining the expression for capital D, here we are making the use of Maxwell's equation here. So on the previous slide we have the 4 Maxwell's equation. So out of these 4 I am making the use of second equation. Second equation, the left hand side in the differential part, thereupon you see it is del bar cross of H bar. So here we can make first of all the use of del bar cross of H bar. So this is the curl operation here. So the curl formulation also we have seen our first chapter. So with respect to the consideration of rectangular coordinate system, here we can express as the given H here is having only one component that we can regard to be Hz here. So here we have the formulation minus del x capital H into Ay here. The substitution gives us it is twice into beta sine of 10 raised to the power 10 into t minus beta into x here, bracket is completed, and here it is multiplied by Ay here. So as per the given problem statement, if we are making the use of Maxwell's equation, I will just get you back to the Maxwell's equation here. So this is what the equation. So when you are putting sigma is equal to 0, conductivity is equal to 0, J is basically equal to sigma into E. So sigma is equal to 0, we will let this J is equal to 0. So we have to discard this. So according to the Maxwell's this equation, del bar cross of H bar will be equal to del D by del T. Now moving further, this was our problem statement and we were here. So del bar cross of H bar, what we have represented as minus of del x of capital H into Ay. Here it is equal to minus twice beta sine of 10 to the power 10 t minus beta x into Ay. So here it is equal to del D by del T here. So here you see for the capital D here, it is having the partial differentiation with respect to the parameter T here. So to get the expression for simply capital D, having this to be the same left hand side to this particular expression, we have to carry out the integration here. So the expression of capital D can be obtained as capital D is equal to the integral carried over twice beta into sine of 10 to the power 10 into t minus beta x dt added by certain constant of integration here. So when we find out the integral solved here, so it will be equal to minus twice beta divided by 10 raised to the power 10 multiplied by the cosine of 10 raised to the power 10 t minus beta x. The bracket is completed and here it is multiplied by ay. So as this is the expression for the capital D is electric flux density. So it has to be measured in terms of coulombs per meter square here. So as per the given problem statement, we were asked to find the derivation, the expression for the capital B then capital D. So capital B expression I have already shown to you people. This is the answer for capital D expression here that you can outline here. Now after the expression for capital D, we require the expression for capital E. Capital E is electric field intensity, and now we know that the relationship between the electric field intensity and the electric flux density is given by the expression. Either you write D is equal to epsilon E or capital E we are required to know. So capital E is equal to capital D divided by epsilon. So capital D expression just now we have obtained in the above outlined form here. So this expression on the RHS part here, we can make a substitution to this capital D here. We will divide it by the epsilon here. Now you check the problem statement. In the problem statement, epsilon value is provided to us, that epsilon value is equal to 1.2 into 10 raised to the power minus 10 measured in terms of farads per meter here. So let us make the substitution. So capital E by the next step will be equal to twice beta divided by 1.2 into 10 raised to the power minus 10, bracket is completed and here it is multiplied by 10 raised to the power 10. Further, this ratio is multiplied to the cosine of 10 raised to the power 10 t minus beta x into ay, and this is all there with a negative sign here. Here you see this is with the negative sign, as the expression of capital D was there with the negative sign originally here. So by the next step, when we have the calculations done, so that the simplified expression for capital E electric field intensity can be obtained, here we get it to the form, it is equal to minus 1.67 multiplied by the beta into the cosine of the bracket where we have 10 raised to the power 10 t minus beta x multiplied by ay here. So as this is the electric field intensity, it has to be measured in volts per meter. So I just outline the expression here. So capital E is equal to this right hand side. This is the required answer to be the expression for capital E. So in this problem statement, we were asked to derive the four expressions concerning capital B, capital D, capital E and beta here. So the first three are done. Now we are left with to find the expression for beta. So here we go. As we have now the expression for capital E electric field intensity, we are taking the help from Maxwell's equation. So for that purpose, the first equation that you have seen on the beginning slide, it was del bar cross of E bar equal to minus del B by del T. So del bar cross of E bar is the curl operation of electric field intensity. So according to the curl operation formulation, we obtain del bar cross of E bar is equal to del x of Ey into Az. So when we put Ey to this particular numerator for finding first of all the partial differentiation and then multiplication by the unit vector here, because the earlier expression you see E is equal to minus 1.67 beta cosine of 10 raised to power 10t minus beta x ay. So this is all ey here. So if I substitute the things, this will be of the form, here I write 1.67 into beta square sine of 10 raised to the power 10 times t minus beta x into az here. So by the Maxwell's equation, Maxwell's first equation on my beginning slide here, this is to be equated to minus del b by del t here. So therefore capital B can be obtained if we have the integration on the both sides. So integration on the both sides will take capital B on the LHS equal to minus of the integral 1.67 into beta square sine of 10 raised to power 10t minus beta x into az dt here. So here solving the integral we get to the form 1.67 into 10 raised to power minus 10 into beta square cosine of 10 raised to the power 10t minus beta x az here. So here we have the expression for capital B. Now we require the expression for beta here. So B already we have the expression at the very first just by multiplying the value of mu to that of the h here. So here capital B is a known quantity. The beta is the unknown quantity. So from this expression, what we can have by substituting the expression that very first of all we had for capital B to the left hand side here, we get it 1.67 into 10 raised to power minus 10 into beta square equated to 6 into 10 raised to power minus 5. So as we have only one unknown, we isolate that unknown on the left hand side. So this equation implies that beta is equal to the phase shift constant plus minus 600 radians per meter. Per meter is the unit for the phase shift constant denoted by beta. So here it is the last value we were asked to determine as per the problem statement. So in the problem statement we required the expression for magnetic flux density capital B, then the electric flux density capital D, electric field intensity capital E, and the phase shift constant beta here. So all the four expressions, the values we have obtained here. So this way problem number 1 is completed here. So after problem number 1, let us have the practice of problem 2. In the problem number 1, out of the 4 Maxwell's equation, we have made the use of 2 here. Now let us again make the use of total Maxwell's equations to solve these particular problems here. So now here the second problem statement starts with the electric field intensity in the region x greater than 0 less than 5, y greater than 0 less than pi by 12, z greater than 0 less than 0.06 meter space is given by capital E is equal to capital C times sine of 12y into sine of az into cosine of 2 into 10 raised to power 10 t ax in terms of volts per meter. Beginning with del bar cross of E relationship, use Maxwell's equations to find a numerical value of small a if it is known that small a is greater than 0. So this is our problem statement. So in this problem statement, we have been provided the expression for capital E. Capital E is the electric field intensity, and this expression is valid true for the region defined by the range of x, y, and that of the z here. So this is the consideration of rectangular coordinate system here. Now the very first expression into the set of Maxwell's equation was del bar cross of E. So it is equal to minus del V by del T for the time varying fields we have seen on the very first slide here. So beginning with the help from this Maxwell's equation, we have to find the numerical value of small a. Small a is the representation in the expression of capital E, electric field intensity at this particular place here. And consideration that small a is greater than 0, so it means it is a positive here. So now as we see that the first equation in the Maxwell set is del bar cross of E bar is equal to minus del B by del T here. So del bar cross of E bar is the curl operation here. So first of all, by making the use of curl formulation, del bar cross of E for the given capital E here. So here you see the unit vector is small ax. So this is completely capital E x here. So we have to express del bar cross of E bar is equal to del z of Ex into Ay minus del y Ez into Az here. Now the substitution here will be as such. I am writing capital C as it is. In the square bracket you have small a into sine of 12y cosine of Az into Ay minus 12 times cosine of 12y into sine Az into Az here. The bracket is completed and here we have cosine of 2 into 10 raised to the power 10 times t here. So this is to be equated to minus del B by del T according to the Maxwell's equation. So when we equate it, so we get the equation modified to the form giving information as such. Capital H is equal to, we have minus 1 upon mu 0 in multiplication to the integral operation over del bar cross of E bar dt added by the constant of integration denoted by C1 here. So here you will be questioning that how the capital B has got changed to H here. You see B is equal to mu 0 times H when it is the consideration of the free space here. So mu 0 if it is multiplied to the capital H, it is nothing but the B here. So we have got them separated here and shifted the mu 0 to the right hand side so that the expression for capital H can be obtained like this here. Now solving the integration here for the del bar cross of E bar as represented in the earlier form, we get the next step for expression of capital H is equal to minus capital C divided by mu 0 into 2 multiplied by 10 raised to the power 10. This ratio is multiplied to the square bracket that has small a into sine of 12y into cosine Az into Ay minus 12 cosine Ay cosine 12y into sine of Az into Az here, and this square bracket that is having the difference of the two terms is multiplied to sine of 2 into 10 raised to the power 10 t. So as this is the expression for capital H being the magnetic field intensity, it is expressed in terms of amperes per meter. So in this expression the capital C1 value is equal to 0. It is the constant of integration. The reason is there is no initial condition put forward here. So by using this particular expression, we have the expression for capital H, we can find out the curl of H here. So the formulation according to the rectangular coordinate system, also known by the Cartesian coordinate system, is given here. So here del bar cross of H bar, the curl of H is equal to del y Hz minus del z Hy. The difference is there and this is multiplied by Ax, the unit vector here. So if we can have the substitution of the two components from the above equation, in the above equation you see here it is the multiplication by Ay component. So except Ay, everything that you see here is nothing but Hy here, and here it is the multiplication by Az. So everything that you see like this is basically the Hz here. So the substitution of these two things to this equation of determining the curl operation here, we get the form minus C divided by mu 0. C is multiplied by 144 plus A square here, whereas mu 0 in the denominator is multiplied by 2 into 10 raised to power 10 here. This ratio is multiplied to sine of 12y into sine of Az into sine of 2 into 10 raised to the power 10 t, and at the last we have the unit vector denoted by Ax. So according to the Maxwell's equation, on the beginning slide I have shown you the set of Maxwell's equation. So from there upon you select J is equal to 0 because of the conductivity equal to 0 here. So it will be del bar cross of H bar only equal to del D by del T here. So while we equate it to del D by del T, we can get the expression of capital D just by integrating the both sides here. And when we know the capital D by the step of integration on both sides here, we can get it converted to the capital E, that it is the electric field intensity, because D bar is equal to epsilon multiplied to capital E bar. So capital E here I write is equal to D divided by epsilon 0 here, and this is equal to the integration 1 upon epsilon 0 as it is, and here I put the D, that is del bar cross of H bar dt for the integral sign here, and here it will be added to the constant of integration denoted by C2 here. So by the next step we get it to the form capital C in multiplication to 144 added by A square. This is all divided by mu 0 epsilon 0 multiplied to 2 into 10 raised to power 10 squared here, and this ratio is multiplied to sine of 12y into sine of Az into cosine of 2 into 10 raised to power 10 times t here, and this is all multiplied by the unit vector Ax here. So in this representation the constant of integration C2 is equal to 0 here. So this is the electric field intensity describing the electric field in general. So this particular field must be the same as the original field as given into the problem statement here. So therefore we require the value from the comparison of both the expressions, capital C into the bracket 144 added to A square, and this is divided by mu 0 epsilon 0 in the bracket we have 2 into 10 raised to power 10, that is squared here. So this ratio should be equal to 1 here. So mu 0 and epsilon 0 are the two constants here. So mu 0 is the permeability of the air or the vacuum. It is equal to 4 pi into 10 raised to power minus 7 Henry per meter, whereas epsilon 0 is permittivity of the free space or air. It is 8.854 into 10 raised to power minus 12 farads per meter, and when you put that particular value and invert it, so it means 1 upon mu 0 epsilon 0. So this much of term is nothing but the velocity of the light in the air or free space or in the vacuum you say. So this is equal to 3 or 8 meters per second. So when we substitute this particular value, so rest of the thing having the only small a to be the unknown here, so we get it to the value of small a by putting mu 0 epsilon 0 like this here. Small a is equal to the square root of 2 into 10 raised to power 10 bracket squared divided by 3 into 10 raised to power 8 bracket squared, and this ratio here we have minus 144 here. So this is giving us the answer 66 meter inverse here. So here we have the outline to this particular value has to be determined in the problem statement here. So after the completion of the second problem statement, I have the third problem statement to practice again with the use of Maxwell's equation here. In the previous equation, in the previous problem also we have used the Maxwell's equation couple of times here. Now again we have one more problem. So the problem statement here it is: in a sourceless medium in which j is equal to 0 and rho v is equal to 0, assume a rectangular coordinate system in which capital E and capital H are functions only of z and t. The medium has permittivity epsilon and permeability mu here. We have part A of the problem statement. If capital E is expressed as EXAX and capital H is expressed as HYAY, begin with the Maxwell's equations and determine the second order partial differential equation that EX must satisfy here. After that, we have the part B to find out. Show that Ex is equal to E0 multiplied by cosine of omega t minus beta z is a solution of that equation for a particular value of beta. And lastly, in the part C, we are asked to find beta as a function of given parameters. So here one by one we shall be having the solution to part A, B and C. So before finding the direct solution here, it is quite essential to understand what is the situation given in this particular statement. At the very first, the medium in which the supposed condition is there. So it is described to be a sourceless medium. There it is no source of the field here, and because there it is no source, generally we say the source of electric field is a static charge in terms of coulombs, whereas the magnetic field has a source of current measured in terms of amperes here. So when there it is no such source here, there it won't be any cross sectional current density. That is why capital J is equal to 0. So this is for no current component, so that the magnetic field is not existing. The current component is not existing, whereas rho v is equal to 0 because there is no static charge. So as there is no charge distribution, there is no electric field. So here it is the sourceless medium describing J is equal to 0 and rho v is equal to 0. Now we are asked to make assumption with a rectangular coordinate system into the mind, where the two prominent vector quantities of the electric and the magnetic field, correspondingly electric field intensity and magnetic field intensity, are functions of only z and t. You see, z is a spatial dimension here, so it is a measure of length. So generally I am preferring the right handed coordinate system, where the upright orientation I prefer for the z axis. So let us say this is the positive x axis, negative x axis, here it is negative y axis, here it is positive y axis, here it is positive z axis, negative z axis here. So this is what the length along the vertical line that you see. This is nothing but the z here, and t is the time parameter. So we have been asked to make the assumption that E and H are the functions of z and t only. Now the medium has permittivity epsilon and the permeability denoted in general by mu here. So here in the part A, we shall focus our attention first of all. If capital E is provided as EXAX and capital H is provided as HYAY. Now you see, Z is the direction selected for the representation of the E and H, in which there is a change here. E is having a variation along X, H is having a variation along Y here. So we have to begin with the Maxwell's equation and determine the second order partial differential equation that Ex must satisfy here. So first of all, we shall solve this part and then we move on to have solution for part B and part C here. So from the set of Maxwell's equation, we pick the first equation here, for the time varying fields. The first Maxwell's equation, there it is, del bar cross of E bar is equal to minus of del B bar by del T here. So from this expression, the curl of capital E is there. So we can make the use of curl formulation used in the rectangular coordinate system, and we can have substitution to the left hand side of this particular expression here. Now in the right hand side we have the vector quantity denoted by capital B. So capital B is the magnetic flux density, and capital B is equal to mu into H, magnetic field intensity. So if I have the representation of B is equal to mu H, so mu is a constant, it can be put outside as the constant out of the differential representation here. So the new form of this Maxwell's equation by the substitutions will get to the form del z of capital Ex Ay is equal to minus of mu into del t of Hy multiplied by the unit vector Ay. So in this particular case, the curl has dictated the direction that capital H is the magnetic field intensity it must lie in. So in the similar case, use of the other Maxwell's curl equation is given by del bar cross of H bar is equal to del D by del T. Already in the given problem statement, we have been discussing the concerned medium in which the things are supposed to be assumed here is a sourceless medium. So if there is no source, so sigma is equal to 0. So that is why the Maxwell's second equation that I have shown you in the very beginning, that it was del bar cross of H bar is equal to J bar plus del D by del T. So thereupon J is basically equal to sigma E. So because of sigma equal to 0, that J is equal to 0, and we are left with only this much of the Maxwell's equation here. Now from this equation, on the left hand side we have the curl operation for the vector H. So if we make the use of the curl formulation that we have in the rectangular coordinate system, we express the LHS as the minus of del z of Hy Ax, and this is equal to, for the capital D electric flux density is equal to epsilon into electric field intensity. So having the multiplication of epsilon with the electric field intensity, and for epsilon being a constant value, taking it outside the representation of the partial differentiation, we have the new form of this equation. So minus del z of Hy Ax is equal to epsilon del t of capital Ex into Ax here. Now differentiation the first equation with respect to the z, and the second equation that we have just now obtained with respect to t here, we get two more equations. So here it is the first equation, and here it is the second equation here. So as I said, we will be having del 2 capital Ex divided by del z square given by minus mu del 2 Hy by del t del z, and the second equation is del 2 Hy del z del t in the denominator. This is equal to minus epsilon del 2 Ex by del t square here. So this equation will give the new form of the equation to this, and this equation will give the new form of the equation by this here. So what we have done, we have differentiated the first equation with respect to the z. So here it is the outcome here, whereas the second equation is differentiated with respect to the t. So here it is what the outcome here. Now if we combine the two equations here, the combined form from the two equations, we get to del 2 Ex divided by del z square. This is equal to mu epsilon del 2 Ex by del t square here. So this is what the required expression. In the part A, we were said that if E is equal to Ex Ax, H is Hy Ay, begin with the Maxwell's equation and determine the second order partial differential equation that Ex must satisfy. So Ex must satisfy this particular equation. So on the left hand side as well as on the right hand side, the vector quantity is Ex only. On the left hand side, you see there it is the second order partial differentiation of the capital Ex with respect to the spatial dimension z, whereas on the right hand side the second order partial differentiation of the Ex with respect to the time as the independent parameter is multiplied by the two constants mu and epsilon, and these the two differential representations are equated in this particular representation here. So this is what the solution to part A of the problem statement here. Now let us focus on to the part B. In the part B, the question it was, show that Ex is equal to capital E suffix 0 into cosine of omega t minus beta z is a solution of that equation for a particular value of beta. So here, as we have to show the expression for Ex to be the solution of the earlier equation for the particular case of beta here, we have to make substitution, and we find here that del 2 Ex by del z square is equal to minus beta square into capital E suffix 0 cosine of omega t minus beta z. And so this is just the substitution that we can make for the left hand side of the earlier equation as the solution for part A here, whereas the RHS, that is denoted as mu into epsilon, so in multiplication to del 2 Ex by del t square, this is equal to minus omega square mu epsilon capital E0 cosine of omega t minus beta z here. So these two equations will be equally provided the constant multipliers of the cosine omega t minus beta z are equal here. So the expression capital Ex is equal to E0 cosine omega t minus beta z is the solution of the earlier equation for a particular case of beta. So this way we can answer to the part B here. Whereas we have the last part, part C here. In the part C, we have been asked to find beta as a function of the given parameters here. So now, if we equate the two constants of the part B here, we find the expression simply here it is beta is equal to omega in multiplication to the square root of mu epsilon here. So this is what the expression for the phase shift constant in terms of omega being the angular frequency, that is equal to 2 pi f, mu being the permeability of the medium, epsilon being the permittivity of the medium. So the product of permeability and permittivity of the medium is shown in the square root further multiplied by the angular frequency. So this was the problem number 3 based on to the Maxwell's equations. Now here we have the fourth problem statement again to practice concerning the use of Maxwell's equation here. The fourth problem statement starts with the statement as, in a region where mu r is equal to epsilon r is equal to 1 and sigma is equal to 0, the retarded potentials are given by capital V is equal to x of z minus ct in terms of volts, and capital A is equal to x of, in the square bracket we have z by c minus t in multiplication to the Az as the unit vector measured in terms of Weber per meter, where c is the velocity of the light, a constant that can also be the value 1 upon square root of mu 0 epsilon 0 here. We have the three parts to find answer for. The first part is, show that d bar is equal to minus mu epsilon del v by del t here. So del bar dot of a bar, I am calling this a bar, it is a vector quantity, or you can represent it from the textbook to be the bolt casing here. So del bar dot of a certain vector quantity is just the representation of the divergence here. So we have the two types of the potential. Type of the potential, the scalar one, here we have represented by capital V here. Now you see it is expressed in terms of only magnitude, not the directional content here. So I call it to be the scalar potential. Whereas there it is another form of the potential denoted by capital A, it is the vector potential here. You have along with the magnitude, there it is the directional content also in terms of the unit vector Az here. So when we have the divergence of the vector magnetic potential here, so this is equal to minus of mu into epsilon multiplied to the partial differentiation of V with respect to the time as a parameter. So this is what the part A question. In the part B question, we are asked to find the expressions for capital B, that is the magnetic flux density, whereas capital H is the magnetic field intensity, capital E is electric field intensity, and capital D is the electric flux density here. And at last, in the part C, we are asked the question to show that these results from the above cases here satisfy the Maxwell's equations if capital J and rho V are equal to 0 here. So from the part B, when we are successful to have the expressions for or the values for capital B, capital H, capital E, capital D, the corresponding field densities here, we have to check whether they satisfy the Maxwell's equations, provided the material medium or in the surrounding there it is no conductivity, there it is no charge here. So let us answer to first of all the part A. We have to show that divergence of A is equal to minus mu epsilon in multiplication to the partial differentiation of V with respect to the time as a parameter here. So very first of all, according to the formulation for the divergence from the chapter of vector algebra, for the capital A, as we have the component in only the z direction here, the divergence formulation can be represented as, here we have divergence of A is equal to del z of capital A suffix z. So we can have the substitution of the capital A suffix z, so that it is x of, here we have z divided by c minus t here. So this particular differentiation of Az will lead to the value x upon c here, and c value is provided in the problem statement, that it is 1 upon under root mu 0 epsilon 0. When we substitute it, we get divergence of A is equal to x into the square root of mu 0 epsilon 0 here. Now next to that, del v by del t. Del v by del t is equal to minus Cx, because in the problem statement we have been provided capital V, the scalar potential here. When we have differentiation of the expression V is equal to x in multiplication, here we have z minus ct, we get it to the form minus Cx only. And when we substitute in place of c 1 upon under root mu 0 epsilon 0, we get del v by del t is equal to minus of x divided by square root of mu 0 epsilon 0. So therefore the observation is that del bar dot of A bar, that is the divergence of A, is equal to minus mu 0 epsilon 0 del v by del t in the free space. So this also implies that this expression is true in the general medium. So in the general medium we are not representing mu 0 epsilon 0, instead simply mu and epsilon. Mu 0 is just to represent the field, the surrounding to be the air medium or the free space or the vacuum. Same is the case for the representation of epsilon 0 also. So this is what the proof for the answer to be of part A here. Now let us start with determining answers for capital B, capital H, capital E and capital D required into the part B here. So in the part B, we shall be making the use of the expression where capital B, the magnetic flux density, is basically the curl of the vector potential A here. So capital A expression is provided in the problem statement here. We can substitute in place of capital A and we can determine the curl. So thereupon we finally obtain capital B, the magnetic flux density here. So curl of A will be of the form minus del x of capital AX AY. So substitution, it will be T minus Z by C into AY. So as this is just equivalent to the capital B from this particular expression that we have seen while learning the potential here, vector potential here. So this is equated to the capital B, the magnetic flux density. So it has to be measured in terms of Tesla here. Next to that, have the relation between the magnetic field intensity and the magnetic flux density as H is equal to B divided by mu. So here it is the case that we have mu 0 for the free space or the air medium. So we have just now the expression for B. You can take it from the left hand side here and you can substitute on the new expression. So we get capital H is equal to 1 upon mu multiplication to the bracket where we have T minus Z by C in multiplication to AY unit vector. So capital H being the magnetic field intensity, it is to be measured in terms of amperes per meter. So this is the answer for capital H. Now from the use of the vector potential and the scalar potential, we are trying to obtain the electric field intensity with the help of the expression where we have capital E is equal to minus grad V. So del V not having any dot or cross symbol in between the quantity with which it is operating, it is simply the gradient here. So minus grad V minus del T of A here. So we have the expression for V, we have the expression for capital A. So substituting here and finding out the derivatives here, the next step for capital E will be equal to minus of Z minus Ct multiplied by AX minus X into AZ added by X into AZ. So this results into Ct minus Z and this difference is multiplied by the unit vector showing us the direction that it is AX, and as this is electric field intensity, it has to be measured in terms of volts per meter here. And at last we have capital D is equal to epsilon into E here. So just substituting the expression from the left hand side on the screen for the electric field intensity capital E and putting it in this particular place, we get the expression for capital D. So here it is epsilon 0 multiplied to Ct minus Z into AX. So as this is the electric flux density, it has to be measured in terms of coulomb per meter square here. So here I outline the answers. Capital B is equal to this much, capital H is equal to this much, capital E is equal to this much, and capital D is equal to this much here. So this is what the answer to part B here. We were asked to find B, H, E and D in the part B here. So this is what the solution here. Now in the part C, the question is show that these vector quantities satisfy the Maxwell's equations provided J and rho V are is equal to 0. So very first of all, we are having the Maxwell's third equation in the point form, that is basically divergence of D is equal to rho V initially, and when rho V is equal to 0, so divergence of D should be equal to 0. So first of all we find divergence of D. So divergence of, in the place of D we substitute its expression that we have obtained. So here it is epsilon 0 multiplied to Ct minus Z into Ax. So the dot multiplication with this particular vector and the del vector here, we obtain it to be equal to 0. So divergence of D is equal to 0 we have obtained. So we can say that the Maxwell's third equation is satisfied. Similarly, in the Maxwell's fourth equation, we require del bar dot of B bar should be equal to 0. That it means the divergence of magnetic flux density. So when we have divergence of B, del bar dot of B bar, So del bar as it is, and putting the expression for capital B here, we find the divergence. So this divergence will also come out to be equal to 0 here. So here we can say that the Maxwell's fourth equation is also satisfied by the given vector quantities describing the electromagnetic field here. After that, for the Maxwell's second equation that I have shown from the set in the very beginning of this live session, so del bar cross of H bar should be equal to J plus del D by del T here, whereas J being the cross sectional conduction density here, current density, it is equal to 0, so it should be equal to del D by del T. So first of all, I will find the curl operation of H by using the formulation in rectangular coordinate system. Equal to del bar cross of H is equal to minus del Z of Hy into Ax. So substituting Hy here, we obtain it to the form 1 upon mu 0 into C into Ax here. So this is given as under root of epsilon 0 divided by mu 0 into Ax, because the C is equal to 1 upon under root mu 0 epsilon 0. The substitution of C will give the form of the curl of H is equal to this much here. Now on other hand, we require del D by del T to be equal to this. So when we find the partial differentiation of D with respect to the time parameter here, we obtain epsilon 0 into C into Ax here. So substituting the expression of C is equal to 1 upon under root mu 0 epsilon 0, we get it to the form under root epsilon 0 divided by mu 0 into Ax. Now you see the RHS of this expression and this expression is the same. So therefore the LHS can be equated to each other here. So del bar cross of H bar is equal to del D by del T. So this way the Maxwell's second equation is also satisfied here. Now at last we require the Maxwell's first equation denoted by del bar cross of E bar is equal to minus del B by del T be satisfied. So when we find the LHS del bar cross of E bar, it is the curl operation. So substituting capital Ex in this formulation of determining the curl operation value here, we get the answer to be equal to minus Ay. And when we find del B by del T, substituting the expression of capital B, so this is also left with Ay. So here also we can equate the LHS of the equation that I show on the left hand side by del bar cross of E bar to del T of B here. So this way the Maxwell's first equation is also satisfied. So finally I can say all the four vector quantities as obtained as the electric field intensity, magnetic field intensity, electric flux density, magnetic flux density, they satisfy all the four Maxwell's equation as I said for time varying fields here. So this way I have found the solution to part A, B and C of the fourth problem here. So in this session I have introduced you people to the set of Maxwell's four equations and the use of these Maxwell's four equations to find solution to the four sample problems here. So here I conclude the today's live session. By the next week I will meet you again. So thereupon I will conduct the last session here. So that will be with the topic Poynting's theorem and wave power. For more details associated to the subject electromagnetic field theory, you can subscribe to the videos that I have on the online platform of Ekeeda. Thank you.